full-time Windows user, and one of the reasons why is that when I do presentations, things just work. Well, today is the first time that things not actually just work. So we had a little emergency computer switch. I'm using this little clicker. We'll see how it goes. But today I want to talk to you about this programming language called Rust. And we're going to talk about concurrency errors and solving them at compile time using Rust. Of course. I'll just walk over here. It's fine. There we go. Okay. What is Rust? So I've worked on Rust for about 5 years now. Rust is a programming language that was originally developed at Mozilla Research, but now it's an open source project. Mozilla is actually a minority in the overall governance, so it's kind of its own thing, but a lot of people have strong Mozilla associations. I'm paid by Mozilla to work on the language. And this question is actually a little more complicated than you might think. Fundamentally, Rust is a programming language, but as we've worked on it, our understanding of it has kind of changed a little bit. So originally, Rust was created because Firefox is like 5 million lines of C++ code or something, and when you get things wrong in C++, bad things happen, like visit the wrong website, and now JavaScript, owns your computer, bad things. And a lot of those problems, in Firefox at least, are the direct cause of C++ being a very sharp tool, and sometimes the sharp tools you cut yourself. So we had this idea, what if we could make a programming language that would allow us to make Firefox better and still have all the same performance that C++ is known for, but not have all the sharp edges that it's associated with. So like historically, that's what we considered a trade-off in programming languages. You have to, if you want something that's safe, you sacrifice speed. If you want something that's fast, you sacrifice safety. And so Rust's answer to that problem is you can actually have your cake and eat it too. Of course, in engineering, there's always a trade-off. I will get into the negatives a little later. Once we start showing type signatures, you'll understand where the trade-off lies. While we sort of pitched Rust originally as this kind of low-level language, and fundamentally it is, when you're programming Rust day to day, it doesn't feel extremely low-level. I actually come from the Ruby world. The last time I was here was for a Ruby conference. I have a Ruby tattooed on my body. Like, I love Ruby. So why start doing this low-level programming thing? There's a lot of different reasons, but Rust sort of feels very high level. And a lot of people call Rust a functional language. I'm not sure what functional programming actually means, so I don't know if it's a functional language or not. I think all these terms are kind of like, have very poor definitions. But Rust definitely borrows a lot of things from functional languages. But one of the big distinctions is this focus on speed and runtime efficiency. Most functional languages are focused on math and type systems, and we kind of have this attitude that like, we'll sacrifice some of that for runtime purposes. So that's enough background on that. Before we talk about why Rust solves these problems for you, let's talk about why those are problems in the first place. So I'm probably going to say concurrency a lot in this talk, and I mean concurrency and or parallelism, but I don't want to have to say concurrency and or parallelism every single time. Parallelism is hard to say. I also mistype it literally every time I type. I'm paid to write English, but I cannot spell the word parallel for the life of me. So these problems, I'm sure I've had lots of talks, like literally the entire last talk, with some degree is distributed systems is hard because of these kinds of things. And sort of we solve them at like a slogan level in programming. And what I mean by this is there's a lot of advice that we have that's sort of like tribal knowledge about how to deal with these problems. So I don't know if any of you have seen this slogan before. Shared mutable state is the root of all evil. So if you have something that's shared and you have something that's mutable, then you're going to run into problems when things happen in different orders, or all sorts of things can happen. Undefined behavior literally means that you don't know what's going to happen. So there's lots of bad things that can occur. However, because this is a slogan, people kind of repeat this without thinking about the details. And so many languages deal with this problem by saying, okay, we're going to get rid of the mutable part, and so shared state is fine. And so if you can make stuff immutable, then you solved one half of the problem, right? And there's not really like that is the solution that people offer. So you have like persistent and immutable data structures, just general, keep things as immutable as much as possible. And that's not a bad solution, but it's not the only one. Remember, it's these two things together that causes the problem. It's not mutability that is actually the issue here. It's mutability plus sharing. And so what Rust does is, Rust says, hey, mutable state is fine. So we have this ability to control how you share things, and that is what provides the sort of concurrency guarantees. And so this is a fundamentally different approach. Because it's so different, we sort of, there was this situation in Rust development before 1.0 when we were working on the language, and we had to decide, do we want to still use this language to talk about mutable and immutable, or do we want to talk about sharing exclusively? And so the problem is that people are so used to thinking about things in a mutable and immutable way, we decided to go with the mutable and immutable terminology, even though that's kind of not actually really accurate. It's hard. It's hard to fight against people's preconceptions. But fundamentally, Rust is about sharing. So how do we actually accomplish these differences? Now works. Cool. Computers. Before we talk about how we accomplish this in Rust, I want to make a brief mention here, which is one of the things that led us to this understanding is that garbage collection is one of the biggest problems why many languages have impossible tasks when controlling sharing. And that's because while GC is incredibly convenient, it allows you to make these connections between objects, and then it's impossible to know who is actually using what and at what time. There's this old slogan about object-oriented programming with something like, you asked for a banana, but you got the gorilla holding the banana and the entire jungle that the gorilla is in. This is the way, maybe this is my time with Rails a little too much, but you kind of end up with these messes of object graphs, and you just kind of let the GC deal with it. And so Rust has no garbage collection, Rust has no runtime, and that's very, very important to accomplish those speed goals, but it also means we have to solve, how do you know when to free memory at the same time? But that lack of garbage collector is really what allowed us to focus in on these kind of situations. And it's also one of the things that makes Rust a little difficult for people to program in sometimes, because they're so used to just being able to create these giant messes of objects and not worry about what happens with them. One of the primary ways that Rust accomplishes this goal, and I put this at the title of this talk as solving concurrency issues at compile time. One thing that's really nice about types is that types are a compile time construct, which means they have no runtime cost. So if we can prove things about our program in the type system, we pay nothing at runtime. And so this is really, really important. Again, in a language that's so focused on runtime performance, the fastest code is the code that never runs, right? So there's a bunch of features in Rust that I'm not going to get into too many of them today. But for example, our version of pointers is called references. We guarantee at compile time that they are not null and they're not dangling and they always point to something valid. And since we do that through the type system at compile time, at runtime, they're exactly the same thing as a C pointer. So you get the same kind of speed and performance, but completely safe instead. The downside of that, as I alluded to earlier, is so when I talked earlier about this speed and safety trade-off, where that problem now goes, you get both speed and safety, you have to deal with some type signatures. You have to start thinking about things in a typed way, and that can be a struggle for people, especially if you've never worked with a language with a very strong type system before. I decided in this talk, the functional programming crowd tends to be a little more comfortable with type signatures, so I have some really scary type signatures later in this talk. You don't write them most of the time, but I thought it'd be fun. Most of the time I'm talking to people who are from Ruby or JavaScript or Python, so I show no type signatures, because that's a little better. Cool. All right. Weird. I have more slides. I'm hitting refresh instead of hitting next. Cool. Yeah! I've been doing this my entire life. I started programming at 7, and I can still just hit the wrong button on the thing, mess everything up. Another thing that's very interesting about solving concurrency errors in the type system is that types are deterministic I wrote this sentence and I was like, there's probably a paper somewhere that has a thing that maybe makes this not true, so maybe this is a lie. But like the type systems that I deal with are completely deterministic. And so one of the difficult problems about debugging concurrency and parallelism errors is that they're almost by definition not deterministic. And so if you can move these problems into the type system, then that means that you can sort of guarantee that these things work, as opposed to, you know, oh, hey, we got this bug report, and it happens only on the third Thursday of the month when there's been this many transactions that happen to go through these specific nodes, right? Like, that's the way a lot of things feel. And you get to the, you know, the runtime sanitizers, which are like fantastic tools, and you should use them in languages that, you know, don't have this kind of type system reasoning. But you have to, like, figure out what is even making the bug happen in the first place. Whereas with types, you figure it out when the compiler yells at you when your code doesn't compile. And so this is kind of an interesting aspect of this solution, is that it moves things from a non-deterministic way to a deterministic way. This also has an interesting side effect where I can't count the number of people that have joined the Rust IRC and been like, hey, the compiler won't let me compile this code. It's totally safe. Why is the compiler wrong? And then I'm like, what happens if you add a thread in here later? And then they go, oh. And so you have to like preemptively think about these issues. So again, nothing is a magic bullet. I don't want to say that this is the best solution to every single problem, but sort of our approach is to front load as much of it as possible, so that way you have a much better time later. And so you know, you spend a lot less time debugging and a lot more time dealing with the compiler yelling at you. I actually like to think about, a lot of people talk about fighting the compiler in Rust. I like to think about the compiler as a friend who's going to warn you that you're about to do something stupid. And so, like, you know, when you're like, I'm going to go jump off that cliff, and your friend's like, maybe that's a bad idea. Like, that's the relationship that I feel with compilers, as opposed to, like, fighting with them. Like, it's there to you know, it's got your back. So, I don't know. So, now we're going to get into actual, like, Rust code, and I'm going to give you a little bit of syntax. I'm not going to cover a ton of the basics. If you've worked in a language that's curly braces and semicolons, you'll probably find this like somewhat reasonable. If you worked in an ML family language, then you know you also might find some influence there. Rust has this concept called traits. This is actually a really bad joke. In the next version of C++, they have a feature similar to traits. They call them concepts. What traits let you do is traits let you define the behavior of something without actually specifying the implementation of that behavior. And so they're sort of like interfaces in many languages, but they're also kind of not like interfaces. Here's an example. The code got pushed to the bottom a little bit because this stuff on the top, Firefox, I don't work on Firefox, so I can say that. So here's an idea of a basic trait. So if we have a trait named foo, and then it has one method named foo, self is explicit, like Python, as opposed to implicit, like Ruby. And it returns I32, which is a 32-bit integer. We could say then implement that trait for a given type. So implement foo for the I32 type and return itself, because it's already an I32. And so then, way down to the bottom here, I don't know if you can see, but the usage is like let x is an I32 equals 5, and then let y equals x.foo. So once we have this trait and an implementation, we can call the method on a particular type. So this is kind of why this like sort of feels like interfaces to some degree. If you may be wondering, like I implemented this trait on a primitive type, it's totally true that you can implement things on primitive types. However, it happens in a scoped and disciplined way, so it's not like Ruby where you sort of implement stuff on things and things happen somewhere else and you know, cry. It's like you have to have the trait in scope for the method to work. So this will only work whenever somebody's imported this trait explicitly. So like if I write this code and you import my library, your I32s don't suddenly have a foo method. So just wanted to also mention that briefly. And so the other thing, though, that traits let us do, it's not just about defining methods. If we wanted to just define a method, there's actually a shorter syntax for that. What traits let us do is they let us bound generic functions. So here, this function foos takes any type t if it implements the foo trait and takes an argument in x of that type t. And then it prints out x.foo is, and then the value of x.foo. And so here, this is the primary way that you provide abstractions in Rust. We don't really have objects or classes. We have structs that have data, and then traits that have behavior, and you combine them and mix them, match them as you want. So it's not like we bundle those two things up into one thing called a class. And so what this lets us do is it lets us write functions that are generic over this behavior without worrying about the particular implementation. Now this is something that happens in a lot of languages, but the implementation is a little different. It's much more like a Haskell or an ML than it is like a C++. So in C++, if you write code like this, it doesn't actually check that the foo method exists on X. It just expands the code out and then runs the type checker. And so you'll get this error that's like really, really large, depending on what you're doing. Whereas we actually check. And so because you bounded T by foo, the only methods you can call on X are the ones that are defined in the trait. You can't call any other methods. And so this gives you like a really strong abstraction boundary where you say like, okay, this is the only place that these things can come from, and we've declared all those dependencies up front. Yeah, you also have to give the name, like it's not any sort of interface that has a foo method. It has to expressly be this foo trait specifically. So if I had a bar trait that also had a foo method, then you couldn't pass a bar to this. It has to be a foo. So strongly typed as much as possible. There's also this other really interesting thing that we sort of stumbled across when we were working on this trait system, and that is traits with no methods. So if the whole point of a trait is to let you call certain methods on something, what good is a trait that has no methods? We call these marker traits, and they look like this. Here's a foo. It's got no methods. So like, why? Marker traits let you say that a type has a certain property associated with it without needing to define a method. So it's kind of like a way of saying a certain thing is true. And then later you can write functions that are bound on that particular property. So not every behavior inherently means you have to do something. Sometimes behavior is just that you exist that way. And so there's a couple of these in Rust in the standard library, and we're going to talk about two of them today because they're related to the topic of this talk. Standard library has two of these. One is called send, and one is called sync. And if your type implements send, then that says a value of this type can be sent to another thread. So we're able to transfer it across a thread boundary. And a type that has sync says that, hey, I can pass a reference to a value across threads. So these two things let you say certain things about the concurrency properties of your types, which then lets you write generic functions that say I can only accept something that is send or something that is sync. So that's kind of the general idea. Before we get into the concrete details, I'm going to show you how this works out in practice. There's one other concept we need to talk about, which is lifetimes. Lifetimes are kind of like the thing in Rust that everybody finds either interesting or scary or both. They're the thing that's most unique about Rust. There's some other languages that have related features, but some aspects of it are actually unique to Rust. And so the syntax is also a little gnarly. We tried to find a better one, and we couldn't, so sorry. What lifetimes do is, well, I have a slide about that in a second. The other thing I want to say before I get into the lifetime details is, when you're writing most Rust code, you don't have to use this feature at all. I wrote the documentation for Rust, and in the Rust book, I don't mention anything but the syntax of lifetimes until chapter 4 of the book, and we don't talk about using them until chapter like 16 of 20. So I'm showing you the like super intense things, but please don't think this is what writing everyday Rust code is like all the time. We're just going to talk about the fun stuff, the hard stuff. So if type parameters let you be generic over some sort of types, then lifetime parameters also are generics, but they let you be generic over scopes of your code. This is why they're a little tricky and tough to reason about, because most programmers, as it turns out, don't really think about the scopes of the stuff that their stuff is being used in. And so thinking about the scope, where your variables are valid and not valid, is a little intense, and then being able to like manipulate that in code is also really cool, but it takes some practice. So let's talk about this in a little more detail. I mentioned earlier we have structs, so structs give you data. So in this case, our struct foo is generic over some lifetime A, so you'll notice the brackets are generic just like we do with type parameters. We also do have lifetime parameters. And there is a value x that is of the type a reference to an I32, and that reference has that lifetime A. We tend to use, just like people use T for type parameter, we tend to use ABC for lifetime parameters. You You can use whatever you want, and I'm going to talk in a minute about one special one with a better name. But just like types, we can have a function that's generic over some lifetime. So x is a parameter that is a reference to I32, and it has some lifetime a. However, because the syntax is, as I said earlier, a little intense, we actually provide certain heuristics where you don't need to write the lifetimes if they can only make sense one way. So for example, here we have one reference, there's nothing else. So there's only one possibility for a lifetime, because lifetimes are a property of references. So why make you write this tick A shenanigans? So in actual Rust code, you would write fn foo x is I32, and that looks a little more reasonable. But that's ultimately a convenience for you as a programmer to not want to claw your eyes out by reading this all the time. Underlying in the compiler, these two things are equivalent. Okay, so here's the problem that lifetimes solve. Let's say we have some value of variable we declare r, and since we declared it here, it's going to go out of scope at the end of this sort of block of code, right? You declare something and it's in scope forever. And then I have these little curlies for inner scope, and so inside that scope, we say, hey, I'm going to make a vector of the numbers 1, 2, and 3, and then I'm going to set r to be a reference to that vector. And then our scope of code closes, and we print out the value of r. So in a garbage collected language, this would totally work just fine. Because r is a reference to v, the garbage collector will keep v alive until r goes out of scope. But in a language like Rust that has no garbage collector, v is going to go out of scope at the end of the curlies, and it's going to deallocate the memory for the vector. So this means we now have a pointer to deallocated memory, which is called a dangling reference, and so this r should print out garbage. However, I made this little diagram to sort of show you the scopes, so you can sort of like visualize it, right? So r lives from where it's declared to where it's used down here, and then v is from there to there, so it's smaller, right? So the compiler, what it does is it looks at these lifetime annotations, and it compares these spans of code, and it says, hey, wait a minute, r and v are connected to each other, but v dies before r dies, so compile time error, this is a problem. So you get an error that looks like this, you don't get an error that looks like that. I thought I had a slide with an error, but I don't. I think it's coming later. The compiler, as I mentioned before, there's this like back and forth with the compiler. We put a lot of work into making good error messages, because especially when you're dealing with like concepts that are a little unusual like this, you need to have really good error messages to help people understand. And so the compiler will even suggest like, hey, did you mean to do this instead? And like 80% of the time, you just do that and your code works. So that's also kind of cool. But we put a lot of effort, and big shout out to the Elm programming language. If you've ever heard of Elm, they sort of inspired us to really take error messages seriously. People really love Elm's error messages, and so they invented ours too. Nice. Okay, so there's also one special lifetime called tick static. And the tick static lifetime basically says this is valid for all time. Like, you may have had like a static, type if you've ever like used that kind of function in a programming language, where you say like static int x equals 5, and it's just available basically forever. Same idea. And so this matters because we start talking about threads. So Rust has native threads. It gives you the operating system threads. It does not give you some sort of green threading. We'll talk about that later. By default, you get the operating system's threads. And so you can't guarantee how long a thread is going to run. And so we need some way to talk about that. So the tick static lifetime is a way of saying like, hey, this thread may run forever, so this reference needs to be valid for as long as possible. And so here's how threads work in Rust. You can say at the lowest levels, like when you want to write some sort of low-level threading code. Here we import the standard thread library, and we say, hey, I want a thread handler that points to a function called thread.:spawn, and spawn takes a closure, so those double pipes are an empty argument list, and then the curlies, the code you want to run in the new thread goes there, and then you join on the handler, and that can fail, so the question mark is our error handling operator. We don't have time to talk about that. But this is the basic idea. You pass a closure to this function, it runs that closure in another thread, and then at some point later, you say, okay, I want to make sure this thread is joined by here. All right, here's our first really intense type signature. So spawn's type signature looks like this. Spawn is a function that has two generic parameters. One is called f and one is called t. F is the argument to the function, and that's going to be a closure. And T is the thing that gets returned as a join handle of T. That's because threads can produce some sort of value if you want them to. So this would be like the return type of the thread. And then we have these three different bounds on these things. So F is bound by Fn once to T. That's the signature for closures. So this says, hey, this is a function. The once part we're not going to talk about, but it takes no arguments because there's nothing in the parentheses, and it produces a T. So this is like, that's a closure type. That's how you know that. And then the second one is the interesting part. Both F and T have a bound of send and the static lifetime. So what this means is any of the types that you pass into a thread have to be able to be transferred across threads, right? That's what I said send means earlier. And tick static means that they have to be alive as long as the thread can possibly run. So we've encoded these two invariants in our type system, and so the compiler can use these to check that we're doing things correctly. We got an example of that coming up. Here's the error message I was thinking of. So here's an example of something you might want to do with a thread. We'll make a vector, and it's going to be mutable, and then inside of the thread, we're going to push another number onto the end. I should have made it 4, but I made it 5 just because. Oh my goodness. So we'll have 1, 2, 3, 5 after this closure runs. But then we try to print out the value of the vector, and then we join on our thread. And so here, we'll get this compile time error, going to cut off a little bit. The way that this, I don't think it's going to be, it's not like scrollable because they're, that's the problem, isn't it? Here. Okay. It's actually, it's funny because on the screen it fits, but because of the projector, it's down a little bit. It happens. Computers. So you get this thing called error, use of moved value v. It moved the closure here, and it complains about the println code. This move, I don't want to talk about it, so I'm just going to like hand wave it. But basically what it says is that you want to take everything that is captured by the closure, and that's required to ownership, as we call the ability to destroy something. It gets moved into the thread. And so what happens, the problem here is if the thread runs first, we would push the 5 onto the end, and then the print would happen and we'd see 1, 2, 3, 5, right? But if the println runs first, we would see 1, 2, 3, and then the push would happen and we get 5 afterwards. So this is something that's like non-deterministic, and is actually what we call a data race. So we have two different threads that are trying to mutably access the same thing without synchronization. This is a data race. This is undefined behavior in C++. Languages like Java go to great lengths to mean that even if you do stuff like this, you'll just get a non-deterministic result, but like still not great. And so the compiler will actually just not let you compile this code. And that's because it can tell there's this interleaving problem between the two things. So we've solved this particular problem at compile time. But you might be asking, like, well, how do I fix it, right? Like, if I want to have a thread add something to a vector, but I also want to print it out, like, what do I do? There's a couple different things. But before we talk about the best one, I'm going to skip over the, like, naive way, which is you can add atomic reference counting and mutex, do all this stuff. That technically works, but it's slow, so I'm going to skip ahead to the better answer. But the problem is, so the previous code we had definitely was not like, it wasn't valid, right? Like, it fundamentally didn't work. But sometimes you have a pattern that's more like this. All I did was switch the last 2 lines. And so here, we join the thread first, and then we try to print it out. So we, personally, as programmers, know that that thread will always execute first before we try to print something out. So this ends up not actually being a data race, but because it's in the type system, and Rust doesn't look at the code you write, it looks at the types that you specify, it will actually still give you the same error with this code. And so this is the downside of pushing things to the type system is, sometimes type systems are dumb, and they don't know that what thing you're doing is actually safe. But the real problem here is that we have an invariant on our function that we don't need. So we're saying that it has to be valid for the static lifetime, but that's not actually true. It just has to be valid until join gets called. But the standard thread interface is too primitive to like understand this, and so we provide the maximal conservative guarantee here. So what happens if you have a problem that you want to do like this? Well, there's a package called scope thread pool, and what scope thread pool does is it gives you something similar to thread spawn, but it doesn't have that static requirement. And so this is how you use external packages for the next couple months at least. We're going to deprecate it so this works automatically and whatever. We can talk about that later. So we bring this pool, a thread pool, into scope, and then we declare a new thread pool with one thread, which is kind of funny. I use this library when I only have one thread because I like the scope aspect of it. So we have our vector v, and then the interface is slightly different. On that pool, you say, hey, I want to start a new scope here. And then that gives you a closure with one argument called scope. And that's kind of the thing that says, like, okay, all the threads must be joined by the time this scope thing moves out of scope. And then it has an execute method similar to spawn that would spin up the thread. So on the scope, we say we want to execute this thread, we push onto the 5, and then that's the only thing that happens in the scope block. So it finishes, and that's done, and everything's good, and the compiler will be happy. And so these next two signatures are even more intense than the previous one. This is, again, not code you actually write. Like, I've been working with Rust for almost 6 years at this point, 5.5 years, and I've never written anything as complicated as this. And part of that is because other people have instead. So you just install a package and use it, you don't have to worry about it. But conceptually, what this signature says is the scoped method has a lifetime for the pool and a lifetime for the scope, and a closure f and some other return type bar. And so the scoped object has this lifetime called pool, and the closure takes in a type called scope that has a reference to that pool and that scoped object, and returns the return type. And then the execute method, which is a method on the scope thing that gets the argument for the closure, it has this scope parameter. So instead of the tick static, we have scope that's connected to the lifetime of the scope object, and so everything just kind of works out. No static here. Again, this is ridiculously intense, but it's showing you how you can code these kind of invariants and then not pay for them in runtime. So this code has no mutexes, no reference counting, no synchronization whatsoever. We're able to do this thing that normally is incredibly dangerous. In fact, if this was an array instead of a vector, that would be on the stack of main. So we'd actually be able to share code across one thread that can have a direct pointer into another thread's stack, and we can guarantee a compile time that you're not going to do something terrible with it, which is really, really cool. This is just the cost. Okay, so we have these types of things. I briefly, before I wrapped up, I want to mention a couple other things around concurrency in Rust, because these interfaces are relatively primitive. You don't want to be manually managing threads yourself. It's not that that's the worst thing, and sometimes you do, but generally you want to be doing something a little higher level. So I mentioned earlier that we only have native operating system threads in Rust. That's true, but in a low-level language, what's cool is you can build your own primitives on top of it. So there's these two projects. One's called Futures, and one's called Tokyo. And Tokyo is basically a green threading runtime built on top of Rust. And so Futures is a thing that's common in a lot of different languages, sometimes called promises as well. You may have heard that name instead. But basically, it gives you a way to say this is a computation that's going to be executed at some time later. So what you could do in this kind of model is you build up a chain of futures. You say, okay, I do this bit of the computation, and then when that's complete, I want to do this other bit of the computation, and then you chain them together, and then you put them into your event loop, and then it runs. And if you've ever done Node, this all makes tons of sense. Or Futures of Tokyo is more directly after a Scala library that does this stuff called finagle. Finagle? I don't know words. Anyway. This gives you concurrency, so it's single-threaded, but you're able to put multiple things on there and have them wait for I/O and do all that shenanigans. And so this stuff is under super heavy development. It has been for the last year or two. We're actually going to put some chunk of Futures into the standard library, so it's not an external package anymore. But Tokyo will always be an external package because not everybody needs to have green threads. So that's kind of interesting. But if you want to be doing concurrent stuff in Rust, this is kind of where the fun stuff is. To give you a little bit of idea of what it's going to look like, right now you have to do it all manually, but we're adding async await to the language, which is really cool. Some people don't like async await, it's totally fine. In the language like Rust at low level, it turns out async await is really important. We can't do implicit stuff for reasons. That's a whole separate talk, or we can talk about it later if you'd like to. Basically, the idea with async await is you declare a function as async, so we have an async function, print1, and then you would await calls to other async functions. Let's let you write code that looks sequential, but actually executes asynchronously. I wanted to put all the code on the slide, so none of this actually needed to be asynchronous. I just did it to like show the syntax. But normally this would be awaiting on some sort of like network call or something like that, right? And so this syntax lets you write this stuff. It's very linear, looks very procedural, but it actually compiles down into a state machine of futures, all that good stuff. So this is, the design for this has been agreed upon by the team, and it's like in a week, if nobody has any last minute objections, the Rust development process basically is a thing where the team makes a decision, there's like a 2-week waiting period. It's kind of like, you know, the like speak now or forever hold your peace kind of like idea. So we're currently in that stage with this proposal. I'm assuming nobody has any last minute revelations, then this will be in the language in a couple months. So that's pretty cool. And it's definitely going to be very helpful for a number of reasons. It makes writing asynchronous code a lot nicer. Okay, I have 2 other little mini announcements, and then we can go to questions. First one is, next year, we're all pretty close to Montevideo, where we are right now. In March of next year, we're going to have the first conference in South America for Rust. So my friend Santiago lives in Montevideo. He's on the Rails core team. If you ever use Rails, that's Santiago. He's been doing Rust lately. And he wanted to start a conference. So it turns out there's a lot of Rust in Brazil, and I hear that the meetup group here had a lot of people recently. So we're hoping that everybody will get together and have a good time. So if you want to see me again, I will probably be there, although I won't be speaking, I'll just be hanging out. So really excited about that. So if this stuff interests you, you know, keep your eyes open. And then I'm also giving a Rust workshop tomorrow. This is going to be starting from 0. All the stuff we talked about today is actually more advanced than I'm going to do in the workshop. It's going to be about understanding the concepts of Rust and getting yourself, you know, writing things. So if this intrigues you at all and you want to learn a little more, that's going to be happening. All right, so that's all I have in terms of slides. Thank you again so much. I also feel really terrible about not knowing Spanish, so sorry the questions have to be in English. Yeah.
¿Alguna pregunta?
My neighborhood in New York actually is more Spanish speaking than English speaking. I'm just the worst. So.
From your talk, it gave me the sensation that some things in Rust, I'm not a Rust programmer per se, are like built on top of each other.
Yeah.
So many times you said like, I show you this, but you don't really do this every day. Mm-hmm. I am an Erlang developer and also an Erlang trainer, and many times I face that same fact in my favorite language.
Yeah.
And I always wonder what will be your answer to this question.
Yeah.
How do you teach the language? You start from the things that you do every day, but then everybody has to learn the deep stuff, or you start from the very inner part and build the knowledge like on top of it?
Totally. So I think that one of the things about this is that every student has a different like preferred way that they want to learn. So I tend to be a very bottom-up person. Like I will learn all the details and eventually move that way. It turns out I'm not most people. And so the way that you do this, we like to think about it as kind of like more like a spiral. So what I kind of do is I generally show, here's the syntax of the stuff that's the same in every language. So here's variables, here's loops, here's whatever. Erlang would be a little different, obviously, but like, you know, okay, similar stuff. And then you sort of like show something a little higher level, like let's build a real thing together using only these basics. And then you kind of drop back down to something more complicated. So you revisit old topics. So if you look at the Rust book, for example, I have a chapter on generics, and then chapter 19 is like advanced generics, where we like come back and revisit the topic, you know, in a more complicated way. And so I think that kind of like spiral or maybe up down is a little better motivation-wise. Because if you know, a lot of people are like, how do I get learning? You know, how do I learn Rust? And I'm like, well, I wrote this book, and they're like, I don't want to read an entire book to like, you know, use a bit, which is totally reasonable, even if it breaks my heart a little bit. So also I think projects like in the middle of learning are very useful. So if you find something that's like, with these concepts we've learned so far, we can build a real thing, and maybe it won't be the most efficient, or maybe it won't be the best designed, but then you can use that later to go back and be like, hey, remember that thing we did was awkward? Now you've learned this new feature that lets you do it in a better way that's like not as bad. So that's kind of the way that's it.
Hi, we talk. I recently saw some talks about C++, telling that if you statically analyze the code, you can somehow infer the lifetime parameters in C++. Could this be possible in Rust?
So, the person who said that about C++ was not lying, but it implies more than is actually true. So about 2 years ago, Microsoft and some others started this project called the GSL, or the, I forget what the title of it is, but some sort of static analysis tools they started developing. And it's great. Like, I fundamentally am not a person that is like religious about languages. I would love to see a safer C++, but in their design documents, for example, they said concurrency problems are not even on the table. Like, we're not even going to try to address that problem. So you can do a little bit of that in C++, but it doesn't go nearly as far as Rust does already today. And they've been working on it for 2 years, and it still is not like totally working. So, so there's those kind of things. I had mentioned briefly about how we have these like patterns that let you not write the lifetimes if you don't want to. I hesitate to call it inference because it's really important in Rust that the type signature is the guarantees that you expect. So we don't want to look at the function body to determine the signature of the function, because that causes problems. So we let you not write them, but that follows like very strict patterns. It's not actually inference. Because inference would mean that you could change the body and now let a code breaks. So we do a little bit of that, but that's the main reason why we don't do full inference. Like, we could also infer the whole type signatures of functions entirely, but we don't, because we think that's a better way to get good error messages and write more robust software. It's not really a technical limitation so much as like a design philosophy. So yeah, we could do more inference, but there's this weird fine line we're trying to walk. Those 3 questions.
Hi, how are you? You mentioned something in the async await part, but I wanted to ask you, which things do you think you had to resign when designing Rust that you feel are important, at least for the moment?
Which things, I missed the what, which things that are what about design?
Which things you had to resign or to left out that you feel are important when designing the language?
Yeah, so this is something that's interesting that I've been thinking about a lot lately because, it's been, so Rust 1.0 is in 2015, so it's been 3 years, and so nobody's perfect, right? So, the thing you work on every day, you want to say it's the best, but then also you look back and you're like, if I'm actually objective about this, there are some flaws. And so one of them is this whole mutable versus not mutable thing. Like, I feel like maybe that was a mistake, and that we got the names a little wrong, because you can actually mutate things that are immutable sometimes, sort of like immutable data structures. So that's like a little complicated. There's some things around, there's a trait called error for error types in the standard library, and it is largely considered a mistake now because there's one function on it that produces an error description, and the type signature we wrote basically means you have to have a static string. You can't do any sort of dynamic string there, and that makes it like nearly useless, and we just didn't notice until after 1.0. So that's like a big mistake. But they're usually on the errors of that, like, oh, this API is not as good as we thought it was. A lot of the stuff that we could add. So, for example, I think that the way that Go does concurrency stuff is nicer as a programmer, but they have a garbage collector and a runtime, so that's an acceptable trade-off for them. So when we decided to have no runtime, that sort of cut off that avenue for the like implicit stuff. So I'd say that's also probably a thing. There's a lot of stuff about Rust that would be easier to learn if we were able to pay those costs when it's sort of against the design decision of language. I think that's the biggest thing for me is like learnability stuff. So the basic thing is part of it. But in general, GC make things easy. I don't think about it anymore. But I don't think that was a bad decision. It's just nothing to be perfect.
Thanks for the work.
¿Alguna otra pregunta? Bueno, aplauso para usted.